Hello class, this is a very brief video about refresher for stoichiometry and mass balances that I think will be useful for addressing the problems that we're going to have. Okay, you'll see the primary acids here: hydrochloric, sulfuric, phosphoric acids, and their molecular weights, along with the predominant bases: sodium hydroxide, sodium bicarbonate, sodium carbonate, calcium oxide, calcium hydroxide, and calcium carbonate. So for water treatment, we're using alum, frequently ferric chloride, ferric hydroxide, and also precipitating with lime in some cases. Alum has a molecular weight of 594 with 14 waters of hydration. And alum ends up as aluminum hydroxide flock, and iron in the ferric state is iron and 3 hydroxide units. Okay, so basic acid-base reactions: hydrochloric acid plus sodium hydroxide, 1 mole of each. Sulfuric acid with sodium hydroxide, 1 mole of acid, 2 moles of sodium hydroxide, so it's a 1 to 2 mole ratio. So when you have alum, aluminum plus 3, then you need 3 moles of sodium hydroxide, so a 1 to 3 mole ratio. So now we're going to discuss a little bit of the stoichiometry related to ion exchange and softening. Okay, so for brine softening, in which the resin is regenerated with sodium chloride brine, you're removing calcium with a resin that has 2 sodiums attached to it. So the sodiums are released into the product water, and the calcium is captured by the resin. That's a 1 to 2 mole ratio. 1 mole of calcium, 2 moles of sodium. You regenerate the resin with salt, brine solution. So it takes 2 moles of sodium chloride to release 1 mole of calcium. Then the calcium ends up in the rinse water that goes to waste. Now for ion exchange, usually have anionic resins and cationic resins. You can think of the anions as being negative, and the word anion is kind of flat. And the cations are the positive, and they have a little plus in the middle. So for removing sulfate, for example, with an anion resin, the resin is in the hydroxyl form, so it takes 2 hydroxyls to remove 1 sulfate. Now, if you're removing the chlorides, then it would be 1 mole of chloride per mole of hydroxide. And in the regeneration, you take the resin that is loaded with the sulfate, expose it to high concentrations of hydroxide ions, usually sodium hydroxide, and you regenerate the resin, and then the sulfate goes to the waste. So for the cation exchange, usually you're taking out the calcium and the magnesium, but also on ion exchange you can be taking out the sodium ions. So that is different from the softening. So you'd have the resin with 2 hydrogen ions attached, reacting with the calcium in the solution and capturing the calcium and releasing the hydrogen ions. Then the resin is regenerated with strong acid, could be sulfuric acid, could be hydrochloric acid typically, and regenerating the resins, and then the calcium, magnesium, sodium, whatever cations you are taking out are in the waste. So a brief comment about combustion. And combustion is oxidation, and this will be a factor that is more prevalent in the wastewater side of things. So the simplest organic combustion is carbon plus oxygen to CO2. Carbon weighs 12, oxygen mole is 32, and you have a 1 to 1 mole ratio. For methanol, which will be discussed later, the molecular weight is 32. It takes 2 moles of oxygen, and you get 1 mole of carbon dioxide and 2 moles of water. So that is a 1 to 2 mole ratio. So 64 grams of oxygen for 32 grams of methanol. So that is 2 grams of oxygen per gram of methanol. So the last part of this little video is how to relate the mass and the concentration in the flow. The flow we're going to be expressing in terms of cubic meters per second, cubic meters per day. We're going to only stay in the metric system, so we're going to be converting flow rates to cubic meters per day usually. Our concentrations are frequently milligrams per liter, so we need to convert those to kilograms or kilograms per day. So there's a million milligrams in a kilogram. There's 1,000 liters in a cubic meter. So for example, if you have 0.06 cubic meters per second, you run through here, and that is 5184 cubic meters per day. If you have 125 milligrams per liter, that is a concentration of 0.125 kilograms per cubic meter. So if you combine these flow rate wise, the flow, the seconds per day, concentration, you end up with 648 kilograms per day. This is a kind of question that you're going to be dealing with time and time again in the class. So hopefully these hints will be helpful to you.